Welcome. This is Math 676. My name is Wolfgang Bangerth. I'm a professor in the Math department at Texas A&M. And what I would like to talk about in this class and over the course of the semester is about finite element methods in scientific computing. Scientific computing is a very broad field. It involves modeling and representing the world in terms of computer programs and predicting things that we cannot, let's say, predict just intuitively. And one of the biggest methods in scientific computing is the finite element method. So what I would like to do in this semester is take a broad view of scientific computing. I would like to introduce you to the finite element method. I would like to introduce you to the tools that we use to represent the finite element method on computers. But I would also like to introduce you to, let's say, common approaches to discretizing partial differential equations with the finite element methods, what to do with the linear systems that come out of this, and so on and so forth. So it's going to be a class that is fairly broad, that involves a little bit of theory, that involves a lot of programming, that involves a lot of knowledge that let's say, gives you a bigger view of this field. And in particular, one of the things that I would like to do is I would like to introduce you to some of the existing software packages that exist out there. So in scientific computing, what you often encounter is that you need to solve, let's say, real problems, not just model problems, for example, the Laplace equation on the unit square, but that you want to solve things that are uncomplicated geometries in 3D, or that require multigrid solvers, or that require higher order methods, and so on and so forth. And it will turn out to be rather difficult to implement all of these things in a code from scratch. And so my goal in this class is, among other things, that I introduce you to the libraries that are out there that you can use for this, and specifically to one of the libraries that implement the finite element methods, and that is a library that I and others around the world implement or develop, that is called deal.II. So let me start with a little bit of an overview of this class and a rationale for why we would want to consider other libraries. So the topic of this class, like I said, was to learn how to solve differential equations on computers, in particular using the finite element method as an example. You will sometimes hear me say that I consider the finite difference method or the finite volume method, these are the two other big methods for partial differential equations, as essentially equivalent to the finite element method. And I think that is generally true, that most of the finite difference and most of the finite volume methods today can be written as variants or as perturbations of finite element methods. So I consider this finite element method as, let's say, an overview, a broader class that contains the other two. So from a practical perspective, partial differential or solving partial differential equations on computers is a very practical field. It is not so much concerned with writing down equations and analyzing them very carefully on a piece of paper, but it has a lot to do with interacting with people from applied fields. So you work with people from nuclear engineering, or from aerospace, or from biomedical imaging, or from the geosciences. And what they often have is that they have equations that need to be solved somehow. And so the role of computational science or scientific computing oftentimes is to take the equations as they come. Whether they're pleasant to solve or not, whether they're easy or difficult, doesn't really matter that much, because we need to solve them because there's an application. And so if you want to do this, you need to have knowledge in a very broad class of fields. So you need to know something about partial differential equations and how they behave. You need to know a lot about discretization, so that means converting an infinite dimensional partial differential equation into a finite dimensional problem. You need to know something about the linear solvers and preconditioners that are involved in this. But then you also need to have a background in programming, and oftentimes programming with very large software pieces, oftentimes thousands, tens of thousands, maybe hundreds of thousands of lines of code. And so for this, you need to know adequate tools. You just can't deal with software at this magnitude anymore if all you know is, let's say, a simple editor, for example. And there are very good tools for these sort of things out there. So this course, Math 676, we'll cover all of these to some degree. I will have lectures that talk about, let's say, the character of differential equations. I talk about different kinds of discretizations. I will talk about solvers and preconditioners. There will be a lot about how to program, how to avoid bugs, how to debug things. And there will be several lectures about adequate tools. So I will introduce you to what we call integrated development environments, IDEs. These are, let's say, programming environments. I will introduce you to tools for visualization. I will introduce you to tools for documenting codes, for example. So this is the field of scientific computing broadly construed, and that is the goal of this class, that I introduce you into all of these aspects. So broadly speaking, the goals of this class is to introduce you to widely used methods in scientific computing, in particular using this software called deal.II. That's a software library that supports finite element computations. I will show you in quite some detail how to use deal.II in practice. So I will introduce you to, let's say, how do you write code, how do you write programs based on deal.II, how maybe a little bit also how internally these sort of things are represented. But then I will also show you modern software development tools, and I will teach you a little bit about software development practice. I think these are very applicable topics that certainly don't just pertain to academics or like me who work as professors, but these are all things that are very important also for practical applications in industry, in the national labs, in many other fields as well. Things that are not goals of this class are that I'm not going to introduce you to the finite element method itself. In particular, I'm not going to talk about the mathematical basis for it. That is something that I expect you to have heard in a class before, or that you have acquired through reading literature. Similarly, I'm not going to show you, with the exception of one single lecture where I'm going to talk about templates, I'm not going to show you how to program in C++. I expect that you already know how to program in C++. And if you don't, it would be worthwhile to take a short course on this, or to take one of the existing books on C++. If you struggle with these sort of concepts, here are a number of books that I typically recommend. So from a mathematical perspective, the book by Sue Brenner and Ridgway Scott about the mathematical theory of finite element methods is sort of the standard book for mathematicians. It is not written for engineers for sure, but it lays out the theory of finite elements and their analysis. There is a book by Dietrich Bräs, originally from in German but translated into English, that's called just Finite Elements, that gives you, let's say, a slightly more applied overview of this, of the finite element method. It is not by any stretch an engineering introduction to this, but I think it is a little bit more, let's say, accessible if you're not a mathematician. As far as for C++, the standard work is by Bjarne Stroustrup. It's called the C++ programming language. Bjarne Stroustrup, incidentally, is a professor in the computer science department here at the same university at Texas A&M, just over there in one of the buildings here on campus. He is the inventor of C++, or let's say the person who originally came up with it in the late 1970s and early 1980s, and of course in the meantime, in the 30 years since then, a lot of people have contributed to it, but he is still the one whose book is, let's say, the standard reference on C++, and is well written. It is certainly a book worth reading if you are not entirely familiar with C++ yet. So let me motivate a little bit one of the big themes of this class, namely that we want to use existing approaches, and in particular existing software in this class, to solve the problems that come out of the applied sciences. So let me start with partial differential equations. Of course, PDEs appear in all sorts of applications. There is, of course, the, let's say, classical applications in structural statics and dynamics. For example, if you want to investigate the deformation of a bridge as a truck drives over it. Or let's say how a road deforms if a truck is on it, how a car deforms if it impacts another car, or maybe how a car deforms as it is subjected to the load from the air that passes it. These are all described as PDEs. Similarly, in fluid dynamics, you can ask the question, for example, how does the water flow around a ship? How does air flow around a car or an airfoil? Fluid dynamics also plays a role, for example, in pipe networks, for example, in oil pipelines. Then PDEs are also used in aerodynamics, flow around cars, airplanes, rockets, and so on and so forth. And so now I've given you the three basic states of matter, namely solid, fluid, and gas. Of course, PDEs also play a role in the fourth state of matter in plasma dynamics, for example, in astrophysics, or when you want to investigate fusion energy. These are described by PDEs typically. These are sort of the classical applications of partial differential equations, but PDEs appear in many other areas that you don't immediately think of. For example, in biology, people use PDEs to model how bacteria migrate towards a food source, for example, or maybe away from areas where there's too many bacteria already. People also use PDEs to model financial instruments. For example, in the 1990s, the Nobel Prize for Economics went to people called Blacks and Scholes, who found out that you can describe the cost or the price that you should ask for stock options using an equation that today we call the Black-Scholes equation. That's a partial differential equation. And then you can apply PDEs to epidemiology, to practically every area you can think of. So PDEs are used in a really wide variety of areas. And what then the role of computational science is to take these equations and solve them. Whatever the people from the applied sciences give to you, this is what you want to solve. And so the goal of this class is to introduce you, to give you a little bit of an overview of PDEs and then how you would approach solving them. So let's say somebody gives you an equation and you need to write the software that solves this. Then there are essentially two approaches. Either you can take a software that already solves this, or you can write it yourself. For many applications, in particular the ones that are listed at the top here, there is standard software out there that's commercially available that solves these sort of problems. So there is software that certainly solves for the elastic deformation of structures. There is certainly software for air and water flow and so on and so forth. So in these sort of cases, there is not much for you to do. You should, of course, use professionally written software that solves whatever application you have. But there are two cases where you have to write software yourself. Namely, if you're somebody who develops computational methods, like me, for example, then there is, by definition, no commercial software out there that already does that. My goal is to develop numerical methods that are better than the ones that are used in the past, or that have been used in the past. And so as a consequence, I cannot use commercial software because that, by definition, does not use the sort of modern methods that I'm interested in. The other area where you have to write your own software is when you have a non-standard problem. So if a biologist comes to you and says, I want to simulate how bacteria move on my Petri dish, then that would be the sort of application where you cannot find commercial software. It's just too small a niche market. Nobody cares about this enough to write a program that might cost $1 million to develop or more, when there's only 10 people in the world who care about this particular application, or who, let's say, who care about simulating this on a computer. And so in these sort of cases, you have a non-standard problem, you need to write your own solvers. So if you encounter one of these two cases, either new methods or non-standard problems, you have three different choices. Either you write something from scratch yourself, or you build something from existing components. So you take a library that gives you building blocks, for example, and you put it together. And the third one would be you start with an application that solves something similar and you modify it. The point I want to make in the rest of this lecture essentially is that option 1 should not be your choice, because it might either be very difficult or it might be time-consuming or expensive. And I think, at least for people like me in mathematics, we often have a tendency to still go with option number 1 because we say we want to control every possible variable. We want to really understand what's going on. But the argument that I think I want to make as part of this class is that we should really not do this, because it essentially means that we spend our years of, let's say, as a graduate student or as a researcher, reinventing the wheel far too many times. Rather, what we should be doing is we should build on existing components, or if there is something that does something similar already, we should just adapt it. So, because this is too abstract, I would like to give you a little bit of an example of why I think that it's worthwhile to build on something existing. So if you look at the three standard tools for the numerical solution of PDEs, this would be the finite element, finite volume, or finite difference method. Basically, all of them have to do a number of steps. So the first thing is that you replace your domain on which you want to solve this PDE by a mesh into, let's say, a set of cells that we call a mesh, or a triangulation. These meshes can be fairly complicated. So on the right here, for example, is an example of a mesh of an underground reservoir. So these meshes can have tens of thousands of cells, hundreds of thousands, maybe millions or even more. And they can have very complicated geometries. So just to represent meshes and to create these meshes is certainly no simple task in realistic applications. Then, by and large, the way you can see partial differential equations is, or let's say a discretized partial differential equation on a mesh, is that you have to define balance relations. Essentially, let's say if you think of flow problems, for example, the balance relationship would be whatever flows out of a cell must flow in on another side. So most of the PDEs that we write essentially come from these sort of balance relationships. And then when you have these balance relationships between cells, you obtain a typically very large linear or nonlinear system that you have to store and solve. Now, every code that has to do with solving numerical or numerically solving PDEs has to do these steps. There's no way around it. And if you are tasked with coming up with a code that does this for a particular PDE, you will realize, of course, very quickly that you have only so much time in a day to do this. And as a matter of fact, you probably also have only so much expertise. Maybe you're an application scientist who knows everything about subsurface flow, but you're not completely familiar, let's say, with algebraic multigrids, or with how to define higher order shape functions, and so on and so forth. And so if you wanted to use modern numerical methods, it would be quite a steep learning curve to come up with a code that shows all of these things in, let's say, in its full complexity today. So what I would like to argue then is, because of these restrictions, that it's worthwhile to look into existing libraries. In particular, because we don't just want to use methods that have been around for 30 years, for example, but we want to use something that is state-of-the-art. So typically, what I would consider state-of-the-art in numerical PDEs today is, for example, that you want to use adaptive meshes, that you want to use realistic complex geometries, higher order elements, multigrid solvers, that this whole thing should scale to, let's say, thousands of processors on modern hardware, and that you want to get output that is suitable for high-quality rendering. And if you see this list, of course, you should ask yourself, well, how is it possible to make this happen in a single code? That is certainly going to take years to implement this, and it is true that if you wanted to implement this from scratch, yes, it would take years. To me, the question whether this is possible or not is not a question of feasibility, but it is a question of how we develop software. So we can ask the question, for example, should every student develop their own finite element solver? Or should they be reusing what others have done in the past? Do we insist on implementing things from scratch, or do we build on existing libraries? And I guess you can already figure what my answer for this should be. I think we should reuse what others have done. And as a matter of fact, there has been quite a shift over the last 10 or 15 years in this regard, where in the past we sort of, certainly in the community that develops numerical methods, we thought that we should just look at model problems and implement things from scratch. This has changed. I think that today we believe that we should be reusing what others have done, because it gives us a better handle on, let's say, you only want to deal with the discretization, but you can still reuse a modern numerical solver for the linear system that others have come up with. Nevertheless, there is quite some, let's say, resistance to this idea of reusing libraries. And what I would like to do in the next few slides is that I go through some of the arguments that people have made in the past against reusing what others have done. And I would like to talk about the reasons for this. So let me actually, before I say this, so just as an introduction to existing software, there are a number of libraries that I will bring up repeatedly in this class. So for basic linear algebra, the libraries that exist is BLAST, that's a basic linear algebra subsystem or subroutines, and LAPACK for, let's say, higher order things like computing eigenvectors and eigenvalues of dense matrices. Then there's the next higher level would be two libraries that are called PETSI and Trilinos that represent vectors and sparse matrices solvers. Both of these support parallel computations, and then based on this we build libraries like deal.II, the library that I'm going to talk about in this class, that do all of the meshing and the finite element parts of this. All right, so to come back to the arguments that people have made against using existing libraries. One of the things that I often hear is that in order to use somebody else's software, of course you have to learn the conventions that are used in there, how it works. I need to read through the documentation. And people say, I'd be much faster if I just wrote all of this myself, because really I only want to solve the Laplace equation on the unit square. And I think the first part is certainly true. You have to learn a piece of software. You have to learn the philosophy that's behind this. But the second part is not true, that you are faster by writing the code yourself. Because today, in these libraries that I just introduced to you on the previous slide, is that there is so much functionality in there, hundreds of thousands of lines of code that you can use, that you don't have to implement yourself. And to just give you an example of this, if you think about how today we use MATLAB, where we just plug and play and we put things together and it all works, we can write code so fast in MATLAB today that maybe they're a little bit slower, but the time to actually come up with a program is so much faster. Essentially, the libraries that I had on the previous slide allow you to do these sort of things for complicated finite element solvers as well. They provide you with the building blocks, and you can just plug them together however you want. Of course, ultimately, what it comes down is this. So if you plotted progress over time for doing it yourself and using existing software, then you could plot something like a straight red line for whatever you write yourself, because you know your speed, you know what time you have. If you were to use somebody else's code, then there would be a learning curve, right? In the beginning, you would be much slower, and because you had to learn how this whole system works, but then comes a point where you become much faster because you can use what you understand is already in there. And the question, of course, is where that crossover point is. And I've been in this field long enough, and I've taught this class a number of times, so I can tell you that that crossover point is at approximately 2 to 4 weeks. If you sit down as a student and all you do is try to learn that software, as opposed to sit down and all you do is write your own software, then that takes you 2 to 4 weeks before you get faster by using something else than if you had to write it yourself. Now, if you think about that a PhD takes 3 to 4 years, then you can immediately see how much faster you would be if you used, or how much more you could achieve if you used what other people have done. So our experience is that if you used these existing libraries, it's quite realistic, for example, to have a PhD thesis that contains or that is based on a program that works in 2D and 3D, uses complex geometries, uses higher order elements, uses multi-grid solvers and preconditioners, and so on and so forth. If you did this from scratch, it would certainly take you 10 or more years to do this. From a faculty perspective, what I often hear is that colleagues tell me that they want their students to understand what they do. And that's why they let them write everything from scratch. And I think there is value to this, to a certain degree, but that if you know how quadrature works in 2D, there's really no way why you need to learn to do it again in 3D. So the answer would be, let them write a toy code where they understand how it works, and then after 3 months, when they do know how it works, they throw it away and start again based on some existing software. Similar argument I hear is that people say, well, you know, I don't know if these packages have bugs. I know that, you know, I can trust my own software. I don't have bugs in my code. And the answer to this certainly is, well, you can't be serious, right? I mean, we all make bugs. Of course your software has bugs. You delude yourself if you believe that you don't. But the real answer, of course, is that the packages that I've been talking about and that I will talk about during the course of this class are written by people who have a lot of experience, who have done this for many years. The software packages have extensive test suites. For example, deal.II runs approximately 2,700 tests after every single change to the code base. And so you can believe that there is a lot more, let's say, certainty that there are fewer bugs in this software than what you probably would be able to do yourself. So to conclude this, when you have to implement software for a particular problem, for example, because you want to develop new methods or because you have a non-standard problem, really try to reuse what others have done already. There are many high-quality open source libraries that do practically everything in scientific computing. And what you will find is that you're far more productive, that you will be able to use state-of-the-art methods, and that your code will have far fewer bugs than if you had to do it yourself. As a final pitch, maybe if you're a graduate student and you're watching these classes, one of the things that I've seen over and over again is that because the time to come up with the first version of a code is so short, so much shorter than if you had to write it all yourself, you will get pictures very quickly. And invariably, it impresses your advisor. So take that as one of the positive aspects of this. So with this, I'll leave this class or this lecture, and we'll cover all of the things that I've talked about in much more detail during the rest of this semester or this course. And I'll come back to many of these issues at a later time.